Welcome back to the next video, everybody. Today, we are going to be talking about the first cohomology group, H1. This will be part one in a series of 2 or 3 videos on H1. So definition, what is H1? So remember, we have a group G acting on an abelian group X, and we usually write the group operation of X additively and the group operation of G multiplicatively. So the first cohomology group, H1 of GX, is 1 cocycles mod 1 coboundaries, much like how H2 of GX was 2 cycles mod 2 coboundaries in the previous video. Okay, what's a 1 cocycle? It's also known as a crossed homomorphism. It's a map from G to X, let's call it F, such that F of G1 times G2 equals F of G1 plus G1 times F of G2. So it's almost like an ordinary homomorphism, but you have this extra G1 here. Okay. And what is a 1 coboundary? A 1 coboundary is a map F from G to X such that there exists a little x and big X such that F of G is G times little x minus X. So you're essentially taking 1 cocycles and modding out by functions that just make Gx equal to X for some X, naively speaking. Okay. So, and I'm going to stop here before I go on and talk more about H1. I want to give you a better and more natural way of looking at cocycles and coboundaries that I think is easier to remember, although you do need to keep the technical definitions in mind for computations. So here's a natural and generalizable way of viewing cocycles and coboundaries. Let's start with 2 cocycles. So suppose F is a 2 cocycle, and let's define big F of ABC to be A times little f of A inverse B comma A inverse C. Remember, little f is a function from G cross G to X satisfying certain properties. So this makes sense. And I like to remember this as like the A here desperately wants to go inside the F and cancel these A inverses, giving us just F of BC, but it can't stuck outside. Okay. And A, B, and C here are in G, of course. So you can check just with a calculation that big F of GA, GB, GC is nothing but G times F of ABC. So that's nice. And so what does the cocycle condition read? Well, if you work it all out, it works out to something much nicer than the cocycle condition I gave you last video. It reads F of ABC minus F of ABD plus F of ACD minus F of BCD equals 0. So you're taking the arguments of big F, you're cycling through them in dictionary order and alternating sign as you go, and you're setting the resulting sum equal to 0. That's very easy to remember compared to the given, like the definition of a 2 cocycle. How about for 1 cocycles? Well, if F is a 1 cocycle, let's set big F of AB equal to A times little f of A inverse B. So it's kind of what we did for 2 cocycles, but with, remove one of the entries basically. Okay, if you work it out, you see that big F of GAGB is nothing but G times big F of AB. And so the cocycle condition reads nothing but big F of AB minus big F of AC plus big F of BC equals 0. Again, you're cycling through the arguments of big F in dictionary order and alternating signs as you go, and you're setting the sum equal to 0. It's the same thing we did for 2 cocycles. How about for 0 cocycles? Well, you can think of H0 of GX as 0 cocycles mod 0 coboundaries if you define 0 cocycles in the following way. So what should it be? So what should a 0 cocycle be? A 2 cocycle was a map F from G cross G to X satisfying certain special properties. A 1 cocycle was a map from G to X satisfying certain special properties. So what should a 0 cocycle be? Well, it should be a map from the 1 point set to X, such that let's say G of X, G times X minus X equals 0. Okay, so what should we do to generalize the above? Well, we don't have many options since F is a map from a 1 point set to X. So let's just set F of A equal to AX. And then you can calculate that F of GA is just G times F of A. And you can calculate that F of A minus F of B is 0. In other words, you take the arguments available to you for big F, you cycle through them in dictionary order, you alternate signs as you go, you add up the results, and you get 0. And this is for all A, B, and G. So this is exactly the same thing we did for 2 and 1 cocycles. So we've described H0 successfully in the language of cocycles. Okay, so how do we think of coboundaries in this setup? Well, in all 3 cases, we can do it the same way for 0, 1, and 2. The coboundary condition just tells us that big F is the coboundary, or shouldn't this be cocycle, of a function from 1 lower dimension. So what I mean by that is, if you were to take the big F associated to a 2 coboundary, just for example, you could check that it took the form big H of AB minus big H of AC plus big H of BC for some function big H satisfying big H of GAGB equals G times big H of AB. In other words, you can associate to big F a function big H satisfying the one cocycle condition rather than the two cocycle condition. Does that make sense? So basically what you're doing is with these cohomology groups, you're taking cocycles and you're sort of modding out things that satisfy the cocycle condition from one dimension down, from one group down. Okay. In fact, I can tell you what big H is in this case. Big H of AB is A times little h of A inverse B, where little h comes from the technical definition of coboundary. Okay. And so you might try to define H3 of GX by yourself. Okay, so the last slide for today, let's talk about the long exact sequence of cohomology associated to an exact sequence of G modules. So let's take an exact sequence of G modules, 0 to A to B to C to 0. So that just means the kernel of one map is the same as the image of a previous map for each of the arrows available here. Okay, so then it turns out there's a long exact sequence of cohomology associated to this exact sequence. And it goes from 0 to H0 of A to H0 of B to H0 of C to H1 of A to H1 of B to H1 of C to H2 of A to H3, to H2 of A to H2 of B to H2 of C to H3 of A to H3 of B and so on. Okay, so it could conceivably go on as long as you like, although in most of the cases we're going to be concerned with, one of these groups here, one of these H1s or one of the H2s will just be 0, and so the sequence will stop at some point. Okay, so for a proof of this, you can see Silverman 1 Appendix B. You can also see Sayre's book on Galois cohomology. You can find this pretty much anywhere you like, honestly. Okay, and so I will begin diving into H1 a little bit more closely next video. So thanks for watching, and I'll see you then.